Greetings everyone. We're going to be talking about angular momentum and rotational kinetic energy. Here I have two different pictures, one of a gyroscope or a top spinning here, and the other is the Earth-Moon system. Both of these systems, angular momentum plays a key role, and so does the rotational kinetic energy that's at play in both of these systems. So we're going to be talking about how do we define both of these and how can we use them to solve problems. Let's start by recalling what the kinetic energy is for just a body that's just translating in space. So by translating, what we mean is that it's just moving and it's not spinning. So we have a mass m and it's just moving in a straight line v. The kinetic energy would be 1/2 mv squared, and we could talk about its momentum. Its momentum would be a vector p, and that's equal to m times v. But now we could talk about more complex motion where we have rotation that's involved. And so we need to talk about where it's rotating around. So here's going to be our pivot or our axes. And then this is going to be how we measure r. And so let's just talk about some point mass m. So this point mass would have, so for our point mass, we're going to have the inertia of this point mass would be m r squared, and we know that omega for this point mass is going to be v over r. So if it's moving like this, v, then we could figure out what its angular momentum is just by dividing this v by this r. So the angular momentum we would find out would be L would be I times omega. And omega is a vector and L points in the same direction that omega does. So if we plug in these values up here, what we get is that I is m r squared, and then now we multiply by omega, which is v over r, and what we get is m r v. So right here we made the assumption that v travel is perpendicular to r. So what we really mean is that L is m r perpendicular to v, or m r v perpendicular. And once you start seeing stuff that needs to be perpendicular to something else, what that really alludes to is that there's some cross product going on. So L is actually r cross mv, or r cross p. So here again we have another right hand rule. And so what we need to remember is the direction of this right-hand rule, and also what this means to the magnitude. So the magnitude of L is going to be the magnitude of this, which is going to be R, the magnitude of R, the magnitude of P, and then times sine theta. So here we have also what is our rotational kinetic energy. And we can continue this basically translation between what's going on in linear space compared to what's going on in this rotation. So m is replaced by I, v's are replaced by omega. So if we just play that game up here, we're going to get I omega squared. And so this is our rotational kinetic energy. And here is our angular momentum of our system. L is equal to R cross P. And there's one more thing I'd like to talk about for angular momentum. So angular momentum, just to remind you, is I omega. And so now let's look at what happens when, what is the torque, and how is the torque related to this angular momentum? Well, torque is equal to I alpha. And alpha, if we recall, is equal to the derivative of omega. So if we just plug this into here, what we're going to find out is that tau is equal to I d omega dt. And so what this tells us is that this is actually d by dt of I omega. But I omega is the angular momentum, so this is dl dt. So here we have torque, which is, so this is the torque that we have on our system, is equal to the derivative of dl dt. And this should remind you of force being the derivative of the momentum with respect to time. And so if there's some system and there's some collision that goes on, we recall like we had some mass m, it's moving at some speed v, and it collides with another mass. Then after the collision, right, that here we had some initial momentum and here we had some final momentum. And because there's no net forces on this system, then this momentum would have to be conserved. So this is also going to be something that happens that we're going to consider, is that say there's some merry-go-round or something like this, and you're standing on the outside of it, and then now you're in a closed system right here. You're going to have some angular momentum, you have I omega, and so if you start to walk towards the center of this merry-go-round, what you're doing is you're changing I, you're changing the moment of inertia of this system. And so that is going to change the angular velocity of this system in order to keep this angular momentum constant. So we're going to see how these things all play together and how they help us solve problems. First, let's start by looking at this problem. So here we have a basketball, and it's going to roll down a hill that has some slope 30 degrees. What is the acceleration of the center of mass of the ball? So let's first think about our forces, and then we need to think about the torques that are on this ball. So the force that we have is mg. We also have a frictional force, and we're going to get to that. So this mg is in a pretty awkward coordinate system for us. Here we have, if we want to talk about how the ball moves down the ramp, it's going to move like this. So this is a nice way for us to talk about the acceleration of the center of mass of this basketball. It's just going to move parallel to the ramp. So we need to convert this mass times gravity, the force of gravity, into this coordinate system, where this is our y and this is our x. So what we do is we draw a little line like this, and then we add two vectors. This one is going to be mg cosine of phi, and then this one's going to be mg sine of phi. So now that we've converted this into an easier coordinate system, now we can talk about the torque that's on this basketball. And what are the sum of the forces that we have? So if we just sum up the forces that we have, just looking in this direction, sum of the forces in our x direction is going to be mg sine phi minus our frictional force is going to be the mass times the acceleration of our center of mass. So here we have also friction is going to be, let's do that in red or something. So frictional force is going to be this way. But here we have a couple unknowns here. We have the acceleration of the center of mass. We don't know that. We don't know the frictional force. We don't even know the mass of this ball. So we've got to dig a little deeper. Let's look at the torque on this ball. So torque is R cross F, and here everything is that nice perpendicular. So when I think about torque is equal to R cross F, then I really need to talk about R perpendicular to F. So, but in this case, is nice and perpendicular. Here's our R. So then the torque on the ball is going to be R times the frictional force that we have. And we also know that torque is equal to I times alpha. So here the frictional force, if we just rearrange this, is going to be I alpha over R. So now we can plug this in to this equation up here. We can use what we learned in torque to help get rid of one of these variables up here. So we're going to have mg sine phi minus I over R alpha equals m acceleration of the center of mass. Now we can use another property, which is that alpha is equal to A over R. So we're going to stick that into here. So this is really A over R. So what this tells me is that this is really mg sine phi minus I over R squared. A, that's my acceleration of my center of mass, equals m ACM. So now I'd like to get all these accelerations onto one side. So A, center of mass, and so I'm going to have my m here, and then now this is going to be plus. I'm bringing this I over R squared term over. And then all of this is going to be equal to mg sine phi. So right now we need to talk about what is this moment of inertia. So here we have a basketball. For basketball, it's hollow, so we look up what is the moment of inertia for a hollow sphere, and that's 2/3 mr squared. So we're going to be sticking in a 2/3 mr squared in here. And then now we can note that there's an m here, there's an m here, and there's an m here. So we can get rid of all of those m's. Well, we can also see that this I is 2/3 mr squared. The m is gone. This r squared is going to cancel with this r squared. So I really have A center of mass is equal times 1 plus I, which was 2/3, and all that other stuff canceled, is equal to g sine phi. So 1 plus 2/3, this is 3/3 plus 2/3, that's 5/3, right? And so now I want to solve for A center of mass, so I need to multiply by 3/5. So this is equal to 3/5 g sine phi. So in this case, I can plug this in, and I'm going to find out that this is going to be equal to 2.94 meters per second squared. So here's where you can stop and do a sanity check, basically. Make sure that nothing went really wrong. If this acceleration of your center of mass ends up bigger than 9.8, then you know you did something wrong. Because if you just dropped this object, if it wasn't falling down a cliff or anything, then it should be accelerating at just g. If it were just sliding down this cliff, then it should go g sine theta. And so what's going to happen is, because it's spinning, it should get even smaller than that. So this value right here should also be smaller than 1, because that accounts for what's going on with your moment of inertia. Some of this kinetic energy gets sucked into rotational kinetic energy, and that's going to slow the thing down. Now let's press this problem a little further, and let's ask, how fast is it going when it gets to the bottom? So of course you could use this, you could do what we did in the last example, look for the acceleration, and then now when you know the acceleration, you look at the distance, and you can use one of those kinematic formulas that we talked about a long time ago. Or you can talk about energy conservation. So what is the energy that we have at the top of the hill, and what is the energy that we have at the bottom? So let's start by talking about what's at the top. So when we're at the top, we just have mgh. We're going to call this our y equals 0 line or our UG equals 0 line. Basically, we're saying that when you get down to here, there's no gravitational potential energy. Or up here, we're going to have MGH. So now we need to talk about what kind of energy do we have in the final case. So it's going to roll down. There's no springs. Gravitational potential energy is 0 down here at the bottom. All we have to think about is the kinetic energy. So there's translational, and this thing is rotating. So we have to think about both of these pieces. So K translational is just 1/2 mv squared. K rotational is going to be 1/2 I omega squared. When we talk about I here, this is a basketball again. It's a hollow sphere, so I is just 2/3 mr squared. And here omega, we're going to be, since we want to know how fast and not how fast is it spinning or something like this, what we want is v. So we'd like to change this omega into a v. So that's v over r. All right, so let's plug in what we know. So here E final is going to be 1/2 mv squared plus 1/2 mr squared, 2/3. And then now v over r squared. Here are a couple things that are going to cancel. One is this r squared. It's going to cancel with this r squared. Then we're going to get this whole thing to reduce down quite a bit. So we're going to have 1/2 mv squared plus 1/2 2/3 mv squared. So here I'd like to group together 1/2 just to bring that out front, and then now I'm going to have a 1 plus 2/3 mv squared. So here's the mv squared, 1/2, 1/2, and then 1 plus 2/3. So this is really 1/2 5/3 mv squared. So now I can solve this. I start off with mgh, amount of energy, and then now this becomes kinetic energy down at the bottom, so 5/3 mv squared. So what I really wanted to do was solve for v. So what I'm going to do is multiply this over to this side and also take advantage that these masses are going to go away. So v squared is going to be equal to 6/5. So that's 2 times 3, that's where I got the 6, and then here's the 5th, GH. So this tells me that V is equal to square root of this. That's our 6/5 GH. And what I'm going to get is 6.26 meters per second. And here again is where you can do another sanity check. You know, if you just dropped this ball, if it fell down, it wasn't rotating when it got to the bottom, what you should get here is a square root of 2 GH. So here you should be checking out, if I got the right answer, that this part, how does that compare with 2? If it's bigger than 2, you know you made a mistake. So you're going to get less and less if it has greater and greater I, basically. It's going to roll slower and slower the bigger that the moment of inertia is. And that's because more and more energy gets caught up into K rotational. You don't just have translational kinetic energy. All right, so let's consider an example where momentum conservation makes our life easier. So here we have a figure skater spinning on her skates, and she's twirling around at this 0.5 revolutions per second. So this omega is 0.5 revolutions per second, and we may want to convert this into radians per second. So if we want to do that, we're going to take a 0.5 revolutions per second and then we need to convert revolutions to radians. So 1 revolution is 2 pi radians. And this is going to give us pi radians per second. All right. So then her arms are outstretched, and she has this for her moment of inertia. If you recall, angular momentum is equal to I omega. And so here we're given her moment of inertia. So this is the moment of inertia. When she brings her arms in, or straight above her head, she decreases her moment of inertia. So this is our final case. So Li is equal to our initial moment of inertia times omega I, and then our final angular momentum is going to be I final omega final. And these two are going to be equal to each other. Because there's no net torque on the system. So then omega final is going to be omega initial times I initial, the moment of inertia initial, divided by the moment of inertia final. So then, well, we can keep this in revolutions per second, rev per second. And then now this is a ratio of her moment of inertia. The initial was 12, and then the final was 2. So this is 6. So omega final is going to be 3 revolutions per second. And so we found her final angular velocity, but how much work did she do? So when we want to talk about work, work is the change in kinetic energy. So her initial kinetic energy, we're going to subtract that from her final kinetic energy. So the final is 1/2 I final omega final squared minus 1/2 I initial omega initial squared. When we plug this in, we're going to get 1.5 joules for initial, and we're going to get 9 joules for the final case. So this leaves us with 7.5 joules. So somehow, when she was spinning like this, she gained 7.5 joules of kinetic energy. So you can ask, where did this energy come from? And you can't just say friction here, because if it were friction, you would expect a negative here. She should be losing kinetic energy. But here she gained kinetic energy. And so work was done on her. And so where did this come from? Basically, she has to do work in order to move her arms from out to in. So you'll notice that if you're spinning, maybe on a swing or something else like this, that it's hard to bring your arms in. And this is why, because if you bring your arms in, you're decreasing this I from initial to final. And so you are having to do work. So if we talk about one of the scenes in the movie Gravity, they're working on this space shuttle, and she's tethered out here, working on some satellite. And then all of a sudden, there's some crash off screen of another satellite that crashes into this satellite. So there's quite a bit of crashing going on. So if we draw out the space shuttle, something like this, and we're just going to do an overhead view or something like this. It's got these nice wings on it, like this. But somehow, when this space debris collides with our space shuttle, it causes it to spin, and to spin really fast at 1 revolution per second. This thing has a huge moment of inertia. So here we can just model this thing as a disk or something like this. So that's 1/2 mr squared, just to make our math easy. And it starts off with some angular momentum, right? It's an initial angular momentum of the space shuttle is 0, basically, because it's not twirling around or anything. But, so this is our top view or something like this, and so we're going to do some axial view. So here's our space shuttle, and here's the wings, like this. And then now, here comes our space debris. And let's just consider that all of the satellite that was destroyed, but we're going to say that its entire mass hits right on the tip of this space shuttle. So this radius is about 10 meters. This guy's mass is about 1,000 kilograms. So this has angular momentum, right? So here's an R, here's a nice V. If we have an R and a V, then that gives us angular momentum, so mvr, right? So now we can use our final momentum, which is, let's just say all of this rotational, this angular momentum got imparted onto our space shuttle. So it had some collision, all of this got consumed by this. And these guys just somehow stopped, just to make everything really easy. That's I omega. This is 1/2 m of our space shuttle, r squared. So let's figure out what this velocity, this guy, needs to be. So this is m of the satellite. We have to be careful with all of these m's. This is the satellite too. And then now v and then r of the space shuttle. It's going to be 1/2 m r squared. And this is the space shuttle too. So now we can just solve for this v right here. When we solve for this v, we get about 500 meters per second. And now you can ask, well, that's not such a crazy velocity for outer space. Why do I call this the most unrealistic scene of the movie? Well, basically it comes down to this assumption. It's that all of this mass just ends up on the very tip. If this thing were destroyed, you'd have pieces everywhere, and maybe this was our situation, and you're going to have pieces hitting here, pieces hitting here, pieces hitting here, pieces hitting here, pieces hitting here. So even if this weren't like so uniform, then you could see that the angular momentum, the total angular momentum here, is still 0, or would be close to 0. So this is the unrealistic part. All right, so let's talk about one more system where angular momentum is really important. So if we think about a day, we think about every day, the time it takes for the Earth. This is our nice Earth. This is the north. This is the south. This thing is spinning like this. At the time it takes for the Earth to rotate in a day, it's 24 hours, 60 minutes an hour, times 60 seconds in a minute. So this is equal to 86,400 seconds in one day. But we have extremely precise clocks. We have quartz from 100 years ago, and we have atomic clocks that are 1,000,000 times more accurate than those quartz clocks were. So we can measure how long it really took the Earth to spin around. If we measure how long each day was, we'd see fluctuations. Every day there's fluctuations on the part of like a millisecond every day. Some days are longer than others. You may feel that way, but in reality this is true. And another thing that you can notice here is that at the beginning of the year, right here, this would be, so this would be January, and then this would be July, is that winter days are longer than summer days. And you might feel that way too. But in reality, it's only about 2 milliseconds. It may feel longer to you. But days fluctuate, so you can say, what is causing all these fluctuations? They're small, right? So these fluctuations are between the core and the mantle. So the center of the Earth is made up of liquid rock, and the way that this liquid rock fluctuates around changes the Earth's inertia. But there's something even bigger going on here. So if the Earth is spinning around here, right? Here's omega. Omega points up like this. Here's the Earth. Is that the moon is also part of our system. So the moon is going around the Earth, right? And so there's an angular momentum associated with the spin of the Earth, but then we also have the orbit of the moon. So this makes up a big system. And we're going to talk about what are the effects that both of these have to play on each other. The bigger effect is between the Earth and the moon. So the moon is some distance r away, and we need to consider the total angular momentum of this whole system. So L spin plus L orbit has to be constant. So the spin is going to be I of the Earth plus omega of the Earth, how fast the Earth is spinning, and then the angular momentum of the moon's orbit is going to be mass of the moon times r, this r right here, let's use the same kind of r, squared, and then now times omega of the orbit. And this all is constant. So now let's consider the effects that are going on. So the moon causes the tides on the Earth, and these tides are pushed by the rotation of the Earth a little bit ahead. And this is because of the friction here. And this friction ends up reducing the rotational kinetic energy. And this is equal to 1/2 I of the Earth, omega of the Earth squared. So if this is decreasing, what has to be happening is that omega of the Earth is getting smaller. So if omega of the Earth is getting smaller, that means that this term has to be going down. So that means that the orbit angular momentum has to be going up if this is to remain constant. The only way that this can happen is that this r is getting bigger. So what this is telling us is that over time, and over a very, very long time, the moon is moving away from us. So we can think about, when is a system going to stop changing, and this is going to happen billions of years from now. But basically, this will stop when the moon is far enough away that each day, so omega of the Earth, right, this is how fast the Earth spins, basically means that a day is 45, well, current days long, or 1100 hours long. And what this will mean is that only one side of the Earth, so this side, will see the moon. The other side of the Earth will never see the moon again. But of course, we don't have to worry about this because this will be billions of years into the future. We can also work this logic backwards the other way, which is that a long, long time ago, the moon was a lot closer to the Earth. And if the moon is closer to the Earth, that means that the Earth had to be spinning faster. And so if we work this back to dinosaur days, then, well, it depends if we're talking about Jurassic or Cretaceous, then days could be just 30 minutes shorter, or maybe about an hour shorter. There are a couple of models predicting different things, but the dino days were shorter. And so this brings us back to the theory of how the moon was made in the first place. And so this one of the leading models is that some rock hit the Earth, and that this rock started off very close to the Earth, about 3 Earth radii away. So maybe about drawn like this, but over time, because of this spin-orbit coupling and the friction of the Earth's oceans with the surface of the Earth, this caused the moon to have to move away in order to conserve angular momentum.